Ellie, you were going to introduce me.
I was just going to say.
Sorry.
You're doing great.
Okay, yeah.
I'm pleased to introduce our next speaker here to discuss the world's smallest computer language, Barry Bird from Duke University, already doing a great job introducing himself. Very excited to hear what you're talking about today.
All right. Yes, Drew University, Madison, New Jersey. Wonderful place. Been there for a little bit of time, 42 years. Right. Okay, so in case you didn't hear me start saying it, there's absolutely nothing practical about the material that I'm going to go over today. You will not be using this programming language in production in any way. It's a curiosity. It's, you know, if you're into the sort of geeky theory stuff that I'm into, then you'll enjoy it. If you're looking for a programming language that you can use in the wild for accomplishing real work, then I suggest you quietly creep out of this session before we get going at the start. And I'm going to say right away that this session could be very boring and very short if you don't, people don't participate. So what I'm going to be doing is presenting some information about this language and asking you to tell me what comes next. And Danny, hey, how you doing? Hello, Danny.
Hi, Dr. Bird. How are you?
Oh, good. How are you? Nice to see you here. Danny, I'm going to count on you to help me out here. I know Danny. Danny, I'm going to count on you to help me out and yell when you know the answers to things. I already told everybody that this is not going to be a practical discussion. It's going to be up in the air, crazy, and then I want people to participate. All right? And everybody help me out. Unmute yourself, talk. All right? So let's talk about languages. Languages can be Turing complete. A Turing complete language is one that you normally call, I guess, a general purpose language. Any algorithm that you want to express can be expressed in that language. Now, a Turing complete language doesn't necessarily have the ability to control a thermostat. It doesn't necessarily even have the ability to write to a printer. A Turing complete language just executes algorithms in and of itself. But the question here is, what does it take for a language to be Turing complete? What does it require? What kind of, the PL1 language was famous for being enormous and having many features. Other languages are smaller. Java was rather small when it started. Now it's got a lot of different features. How small can a language be? How teeny can it be so that we can do everything that you'd possibly want to do in any kind of an algorithm? That's the question here. And I guess, well, what's a language going to have in order to do what a language is supposed to do? I guess one thing we'd say is it has to have some kind of branching. If A is greater than B, then maybe so. It has to maybe have some kind of looping. While A is greater than B, do such and such. How tiny a language can we get away with? Well, I'm going to show you a language that has only 3 statements in it. Only 3. And it turns out that if we stretch our muscles, we can do anything that's possible with other languages in this language. Now, again, we're not going to do things like write to a printer or write to the screen or display graphics. That's not within the purview of Turing completeness. Turing completeness just means that we can stretch our muscles in terms of algorithmic decisions. let's take a look at the language first. There's all there is to the language. And I'm going to move myself over to the other side of the screen. I hope you can see that. Is everybody aware of the feature of Zoom where you go from gallery view to speaker view so that you can see my screen in the large? Or do I need to make this larger?
Can see it fine.
You see it? Right? Everybody can see it?
I can.
Good.
Yes.
Who else? Yep, we're good?
Yep.
Right. This is a language called Unbounded Register Machine. It has only 3 things that you can do in it. You can add 1 to a variable, you can subtract 1 from a variable, and you can keep repeating as long as a variable is not 0, and that's it. That's all you can do. And what I want to do is convince you that you can do anything in this language that you can do in any other language with great effort, with great strain. You can't do anything easily, but you can do everything you want to do. And now I see that at least in my tile, here, you know what I'm going to do? I'm going to put myself over here, and I'm going to do that. There we go.
Barry, just a quick question, which maybe you'll get to, but couldn't the first 2 be combined into just identifier plus equals any constant?
But we don't want to do that.
Isn't that one less statement?
Oh, wow. Oh, that's one less statement. But that means that that statement is more versatile than the one that I have here.
Okay, got it. Okay.
I want to do as little as possible. I want to minimize to almost nothing my ability in the beginning, and I want to march onward from there. Okay. Now that you've gotten the idea of the endeavor that we're going to pursue here, if you feel like, oh my God, why would I ever be interested in that? Then just feel free to log off. I won't be offended. I realize that this is very, very specialized kind of talk that's only for those of us who get goosebumps when we talk about these theoretical things. Anyway, the only thing we can do in this language is add 1 to a variable, subtract 1 from a variable, and we can't even test. We don't have an if statement. We're not going to need it. We can't even test anything but when a variable is or is not equal to 0. That's all we can do. Oh, and one other note, it says at the bottom, x minus minus is x minus 1. That's not a misprint. Minus means subtract 1 if you can. But if you get to 0 and you try to subtract 1, just leave it at 0. We don't have negative numbers in this language. We can't afford them. Negative numbers are for rich programmers. So there we are. That's all we got. And what I want to do now is play the game where I show you that from this incredibly meager set of statements, we can build our way to many, most, all of the kinds of constructs that we do in any real life programming language. Again, if you joined us late, don't do this at home. Don't use this programming language to create anything practical. It'll drive you nuts if you try to do that. I, in fact, did at one point write a compiler for this language. It was fun to do, but it's nothing that I want to use in practice. All right. Before I go on, are there any questions, responses, reactions, thoughts, comments, disgruntlements?
I of course think of how you declare variables or how you get the variables in the first place to do your actions on. Is that not a...
You don't have to declare a variable, just use it. And you have as many as you want. Why bother declaring variables? That's something that these newfangled people invented after BASIC came along. I don't even think Fortran, oh yeah, Fortran declared variables, right? But other languages don't. Oh, every variable starts at 0. Okay. Carl, does that address your issue or partly?
Partly.
Okay. Can you elaborate more on your concern?
Well, if you want to write a program, assuming that you can with this, just like you can with any other Turing programming language, you're trying to manipulate data. So my question is how it gets in there in the first place.
Oh, how it gets in there is not my concern. Okay. That's something, by the way, that Turing completeness doesn't worry about. If we wanted to, we could add a read statement and a write statement to this, and that would take care of all that. But that would be for those of us who think in play languages like this and pure terms, we don't want to dirty up our language with that sort of thing. Okay. All right. So I think I have another slide here that just, okay, so remember now we have 3 kinds of statements. We have add 1, we have subtract 1, and we have as long as a variable is not equal to 0. And when we subtract 1, if we try to subtract from 0, we just get 0. Okay, and that's it. And a register, what's called a register here is really what I'm calling a variable. So any algorithm can be implemented in this language. Any algorithm. So let's see. How do I assign 0 to X? Remember that you have 3 statement types. You can keep going until a variable is not equal to 0. You can subtract 1 from a variable. So this is the statement to assign 0 to X. And I know I said that every variable starts off at 0, but once a variable gets beyond 0, I want to be able to bring it back to 0. So this is the way we're going to do it. Okay. Here's the trick now in this talk. What's going to happen now is that I'm going to feel free in subsequent slides to use the phrase assign 0 to X, because I know that I can do that. So later on, instead of saying while X not equal to 0, X minus n, what I'm going to do is just say assign 0 to X. We kind of remember that we could do that. It's on an earlier slide. We plug that in, right? If we need to. Is everybody good? I see a nod from Carl. How is everybody else feeling?
You're good.
All right, here we go. Here we go. Here we go. Danny says yes. Okay, thank you, Danny. Here we go. How do I assign 3 to X? Well, now you know how I assign 5 to X, or 20 to X, or 30 to X. I'm not going to worry about assigning fractions to X. We have to, if we wanted to do fractions or decimal numbers, we could do it, but we'd have to kind of encode them as integers. It's okay. The theory says, Barry, don't worry about that. I have the backing of some very intelligent people on this theory. Alan Turing, Kurt Gödel, and some others. Alonzo Church. They're very smart people, and they say that this is okay. All right, so I remember that I don't want to do negative numbers either. I don't need them. I can encode them as positive numbers. All right, so I know how to assign 0 to a variable. I know how to assign 3 to a variable. Here's how I assign an arbitrary variable whose value is whatever, y, to a variable that's called x. If I already know that y is 5, how do I make x be 5? Here you go. Now, while you're staring at that for a minute, I'm going to open up another window on my end because I'm discovering that it helps if I can see the slides ahead of time. So where did it go? Come on, PowerPoint, do your thing. Oh, there we are. Okay. Yeah, so look what's happening here.
Barry, is the purpose of the second loop there just to restore the original value of y?
Yes. And boom. So the first loop brings, the first loop takes y and makes it go downward until temp has the same value as y. And the second loop makes temp go back to 0 and y go back to from 0 to its original value. How about that? Well, this doesn't convince me that I could do everything that I'd want to in this programming language, but we're getting started. We're creating a vocabulary of things that can be done. And, you know, right now it's kind of a small vocabulary, but we're going to move on further and get to do more things. Anyway, I'd just like to take a survey here and find out, for everyone who cares to answer the survey, does this make sense to you? Carl says yes.
Yes.
Yes, says Mike, was it?
Yes, it was, Mike.
And Garrett says yes. And Aaron says yes. All right. So let's try thinking about something else. I just managed to take y, whatever value it is, make a copy of it, and put that copy in a variable named x. In the meantime, I had a temp variable that was just used as an intermediary. And in the second loop, what I did was I brought y back to where it had started so that I don't destroy y in trying to make x be equal to y. How about if we try doing this? How about if we try adding y to x instead of assigning y to x? Would that be easier than this or more difficult than this?
I'd say easier because you would eliminate the assign 0 to x, and otherwise it would be identical.
Okay. Everybody else feel the same way? Let's try it. Now, Mike, you suggested that it would be easier.
I figured it would be exactly the same as the previous routine, except
Okay.
you wouldn't start x at 0. You would leave x at its original value.
And that would work, and I did it a slightly different way here. Okay, can we do more than this? Can we add y and z together and assign that to x?
Initialize x to 0, then add y to x, then add z to x.
Initialize x to 0, then add y to x, then add z to x. That's one way of doing it. Let me show you my next slide if I can find it. Ah, there we go. So I already found out how to assign y to x and how to add something else to x. So if I do that, that's like taking y plus z and assigning it to x. Let's try something next. Let's try an if statement. Now, you know, there's no if statement in this language. There's just a while not zero. So I need to kind of manufacture an if statement. And the first kind of if statement I'm going to create, I'm looking over here at my next slide, is if a variable is greater than 0. I'm going to try to create that. And the question is, how? Remember, in a general language, in a general purpose programming language, I would say if x is greater than y, if y is greater than z, if x is greater than y, or y is greater than z. I'm going to do that later. I got to wait for that. I got to build this up piece by piece, baby steps. So what I want to do next is, if x is greater than 0, then do this. And Mike, you probably already figured out a way to do it because you've been chiming in so much. Anybody else got some thoughts?
That's essentially one of your basic 3 statements. You do something while the variable's not 0. So if by definition your numbers are either 0 or greater than 0, you just keep doing it as long as it's not 0, and that's already your conditional statement.
Right, but now I only want to do it if x is greater than 0, not while x is greater than 0. Only once if x is greater than 0. You see how confining these 3 statements are. I'm proud of that. I'm proud of how difficult it is to write in this language. We have to obey the rules absolutely, completely, and strictly. And, you know, I guess it's the old adage, whatever doesn't kill you makes you stronger.
Couldn't you use the while x is not 0, as Carl had suggested, and in the body of the statement you're going to execute set x to 0?
Let's do it. Now, by the way, Mike, the only thing you said that I want to just caution you against is you don't want to mess with x. You said in the body of the while assign 0 to x. We don't want to destroy x by checking it, okay? So we want to have a temporary variable. We assign x to the temporary variable, and the temporary variable is the one that we decrement to 0.
So x isn't quantum, you can't destroy it by reading it.
You should not be able to destroy it by reading it right. Correct. And thank you, that's a plug for my next talk, which is quantum computing. And by the way, thank you everyone so far for sticking with this extremely geeky talk. So far. How far are we going? What time are we going to today for this talk? I knew that and I looked it up, but I didn't.
12:15.
12:15, okay, all right. Let me see what we got next here.
Hello?
Yeah, hello. It should not be too surprising that we can subtract y from x. And let's see what we've got there. We don't want to destroy y in doing this, so we assign y to a temp variable. Now we take the temp variable and we keep subtracting from it while we subtract from x.
Why do you need to say if x is greater than 0?
You don't. You don't. Because remember that when I subtract from 0, I get 0. So it says, strictly speaking, the if statement is unnecessary. And if you're going to ask me, why do I have it there? I honestly don't remember. We're building a vocabulary of statements, starting with as minimal a set of operations as we can. And I guess one of the things, let me, while I'm thinking of it, tell you some of the background of this kind of exercise. We want to know what computers are capable of doing. We want to know what rigorous procedures are capable of doing. If we try to analyze that using languages like Java or C++ or Python, then we have an enormous number of possibilities that we have to analyze. Is a C++ program as capable of doing things as a Java program, or as capable of doing things as a Python program? What's the limit of the capability of languages like this? It's much easier to approach that question when the only cases you have to deal with are add 1, subtract 1, and while not 0. So the reason this language was designed was not so that programmers can go ahead and write useful code in the language, but so that you could take any programming language like Java or Python and analyze its capabilities without getting lost in the many syntactical features of the language. And it turns out, in the theory, to be very useful for that. Let's see what we got next. How about, okay, so earlier on, we did, let's go back here for a second. Earlier on, we did if x is greater than 0. How would we do if x is greater than y? Mike, if you got an answer, hold off, okay? I know that you're, I know that you're you're a step ahead of people. So I want everybody else to just kind of be thinking about this. I mean, I'm going to be a school marm in that sense. I'm going to, you know, kind of, let's not hear from all the time from the same people in the class.
No problem, Barry.
Okay. So I know how to do if x is greater than 0. How am I going to do if x is greater than y? And the answer is start by subtracting y from x and putting the answer in temp. And then ask if that gave you 0. And if it did, then execute the statements that you want to execute and drop out. Since it's an if statement, not a while statement, we want to immediately assign 0 to temp so that we don't keep going, do more than one loop iteration.
Now, what if y is more than x?
Then when we do a subtraction, we'll get 0. Remember that our minus minus doesn't let anything go below 0.
Right.
So our subtraction, when I subtract 5 from 3, gives me 0.
I see what you're getting at.
Okay?
Yep.
All right. Let's try something else. Oh, let's do Booleans. Yeah, true and false. We're gonna let 0 mean false and 1 mean true. And we're going to do an AND operation. You know, we got to build up all these language features. We got to convince ourselves that that we can do anything we want. And by the way, just again, another side note, this whole procedure of saying we're going to convince ourselves that we can do anything we want by showing how many different things we can do has a major flaw in it. I'm showing you, oh, look, I can do if x greater than y. And in the next slide, I'm going to show you, oh, look, I can do an AND operation. And that's really nice, but it would take more, really more, to convince you that we could do everything, because the appearance of everything is not always everything. So that would be another level of sort of stuff that we would have to do if I were to really prove to you for sure that we could do everything in this language. Historically, back in the early part of the 1900s, Bertrand Russell wanted to prove that you could do everything with mathematical logic. So he and Whitehead wrote 2 volumes showing all the nice things that you could do. And it's an incredibly unreadable category book. It's just, it reads like a phone book of things that you can do with mathematics, just with strict logic. And, you know, 2 volumes, and it's just got 1,000 things you can do with it. And it turns out that he was wrong. You can't do everything with logic. So this approach of building up one statement after another. Oh, look, we can do if X greater than Y. Oh, look, we can do if Y and Z, if this is true and that's true. It's a kind of a flawed argument, but it's okay. It's still fun. It's fun for me. Here we go.
So to do your Boolean, okay, I'm sorry.
Oh,
ahead.
yeah. You had a thought?
I'll just see what you've done.
Okay. I just put an if statement inside of an if statement. And I was able to do if something is greater than 0 on an earlier slide. And so I can do that with Y and I can do that with Z. And now X then becomes 1, true, only in case both Y and Z are true. Carl, is that what you were going to mention, or is that kind of what you were thinking? Or
Mine was less elegant. I was just going to add the two together, and then I could have a temporary value that I raise up to 2, and then if basically the sum is 2, then I know it's and, or if the sum is 1, I know it's an exclusive or.
there are a whole bunch of things a whole bunch of ways to do these things now. We have enough of a vocabulary so that there are different strategies for working each of these problems. I don't know that yours is any less elegant than mine. It's all good. Let's try what's on my next slide here. Oh, or. How would we do or?
Could you do assign 1 to X, and if Y is 0, if Z is 0, assign 0 to X?
Yeah, and I did it exactly the opposite way, but exactly the same strategy, but I just started with assigning 0, so boom. So I first made X false and then said, hey, if either of them are if either X, Y, or Z are 1, then assign 1 to X. Change my mind. So you see, we've built up an enormous, we've built up a modest but maybe convincing catalog of things that can be done in a language that starts off with a tiny, tiny, tiny number of features. And I'm a short person. I'm only 5'5", so I like small things. And so this is kind of an interesting exercise for me. I'm going to finish up by asking you the following question, which may or may not be answerable without our getting out pencils and papers. But this is my question. And I'm going to remain silent for a few minutes, if that's at all possible for me to do, while I let you think this over. This is, by the way, not something that we can, that we necessarily will be answering. I don't know. I'd be curious to see what you think about this.
Did you want the answer in the chat box or?
What?
I said, did you want the answer in the chat box?
Answer wherever you want. I mean, the chat is, I tend not to look at the chat boxes in these things.
Yeah.
Unless somebody says that I've got to.
Okay.
What do you think? Any thoughts?
I can't give you a reason why, but my gut says they would be equally powerful.
Okay, all right.
In the same way, I haven't convinced myself absolutely, but I mean, it's missing the subtraction. But since you can subtract all the way down to 0, there should be a way to do some incrementation to find out when to drop down to 0. So intuitively, it seems like it would work. I just haven't proved it to myself.
Okay. So I'm going to leave this as a, a thought thing. And my email, in case you're interested in telling me what you think about this or asking further, is barry@bird.org. And I am Barry Bird, and I work hard at Drew University, really hard, as Danny can tell you. And I'll be happy to hear any comments or questions that you have via email, or if you have any remaining thoughts.
I have a question where you did the example if X is greater than Y, and
Yeah.
you subtracted them to see if it went to 0.
Let me find it. Hold on. There it is. Yeah.
Would you still have a way of doing if X was greater than Y, if the subtraction operation in the language was a true subtraction that could go below 0 instead of a minus?
I tend to think, my gut is telling me that the fact that you don't have negative numbers makes it harder for this language to be Turing complete. But you're right, there is an issue there. I'd have to think about that. It would be interesting if the restriction that we have only non-negative numbers and no negative numbers is part of if that restriction is what makes this work. In other words, that the language is richer because we don't have negative numbers. That's an interesting question. I haven't thought about that. Any other thoughts or questions? Okay, folks, I thank you so much for joining me for this tour into crazy land. And I hope that you'll stick around for other talks during today's Trenton Computer Festival that's being held in virtual Trenton. Thank you again. We'll talk to you soon.
Thank you, Barry. This was very interesting.
Thank you, Barry.